Welcome to my house. Welcome to the Structure Talk podcast, a production of Structure Tech Home Inspections. My name is Reuben Saltzman. I'm your host, alongside building science geek Tessa Murray. We help home inspectors up their game through education, and we help homeowners to be better stewards of their houses. We've been keeping it real on this podcast since 2019, and we are also the #1 home inspection podcast in the world, according to my mom. Welcome back to the show. Tessa, great to see you. I am excited that we're finally getting around to this topic. I teased this a couple episodes ago. We said we were going to get somebody on to talk about heat pumps. Didn't we kind of talk about it on the air? We kind of brainstormed like we need to get an expert on about heat pumps. And I think we talked about Pat Huelman in the middle of our podcast. We said we got to reach out to him and see if we could get him on a guest to talk about heat pumps. Because I'm kind of incompetent when it comes to these things. And Tessa,
same.
Who'd you get on?
Everybody, happy to announce we have special guest Pat Huelman on today with us.
Woo!
Hi, Pat. Welcome.
Hey, hi all. Yeah, glad to be back.
Good to see you. Well, Pat, you when we reached out to you, you're initially like, I'm not a heat pump expert, but I have to tell you, sitting through some of the classes with you this past semester, teaching building science at the U of M, you touched on heat pumps, and you know way more than you give yourself credit for. You understand all the history, you understand the future, the big picture, and you understand the minutia, like the mechanics of actually how the systems work too. So don't sell yourself short. We are really happy to have you on and kind of pick your brain today about heat pumps.
Yeah.
Well, it's fun to be here. And like I said, I feel very comfortable at the high level. I can go pretty deep, but there's a lot of things happening pretty fast and quick in the field and, in the whole area of heat pumps. And so it's a moving target for sure, but let's kind of look at the big picture and what we have today and where it might be headed.
Well, Pat, to start off, can you just explain to us what is a heat pump? I mean, my basic understanding is it's an air conditioner that runs in reverse, but help me understand a little bit more about that.
Exactly. Yeah, that's irony, is that we've had heat pumps around us for a long, long time. So let's go way, way back here. So in nature, things always go from more to less, high energy to lower energy, from warm to cold, from water runs from high to low, downhill. So let's take water. So you have water and in the ground, and you'd like to get it up to the surface or maybe into the water tower. What do? You use a pump. You pump it. So you have an impeller, you have a motor, and some external energy that runs that motor, runs the impeller, and is able to pump the water up against nature. So that's what a heat pump's doing. So remember, heat is always flowing from warm to cold. So how in the world does you take the heat out of your cold refrigerator and put it into your kitchen? It's just warmer, right? The kitchen's warmer than the refrigerator. How are you getting that heat out of the refrigerator, out of the food that you put in there, and pass that off to the kitchen? You have to have a pump. In this case, it's a heat pump. There'll be an impeller, we'll call it a compressor, and then we add a refrigerant that can be compressed and condense and expand. And we got to have external energy, in this case electricity generally, to run that pump, to pump from cold to warm. So what happens in you said air conditioner, what's happening with an air conditioner? We're taking heat out of our house, we'll call it 75 degrees or 72 degrees, and we're putting it outdoors where it's 90 degrees. How do you do that? Nature doesn't allow that to happen. Well, we use an air conditioner that uses a heat pump to pump heat from the warm to the warmer, or cold to warmer, right? Against nature. So the same thing happens. I guess one other thing I missed here is, everything has energy down to absolute zero. So the air has energy in it till it hits 460 some degrees below zero. And so even in the winter, there's air out there with heat in it. not very much, and we don't.
Yeah.
It's not comfortable, but we can extract heat out of that cold air with the heat pump and pump it into the warm space, now the house. And typically you're going to pump it up to 100 degrees or something like this to send it down your ductwork to get to your room and be 75 or whatever it is you want for your space temperature in the heating mode. So that's really what a pump is, and it's all around us. Like I said, it's in your refrigerator, it's in your freezer, it's in your air conditioner, whether it's a window air conditioner or a central unit. Same thing's happening. There's this compressor that has a motor on it that uses external energy, electricity, to pump between a condenser and evaporator. Those are terms that kind of represent the two sides. One's taking the heat and one's giving up the heat, and they can be switched. The air conditioner, in a sense, simply takes a reversing valve, and we can take an air conditioner and reverse it and take heat from outdoors and put it into the indoors. So you think about an electric car. How's an electric car getting heated? And it doesn't have warm water in the radiator. It's not taking heat off the electric motors like we would with a gas car. So it has to have a heat pump. And even our regular cars, gas powered cars, have an air conditioner. Same thing. There's a motor running a compressor, and it's taking heat out of the car and pumping it outdoors. So it's all around us, and heat pumps are just going to be more and more prevalent in our lives in the future. There's just no way around it. It's a very clever system, very clever device to move heat against the kind of the natural laws or nature's laws.
And so if I'm doing a home inspection and I see your traditional air conditioner, split system air conditioner, half of the unit sits outside. It's that big box on the outside of the house. The other half of it sits on top of the furnace. That's the evaporator coil, the part that grabs heat. If I'm looking at an air conditioner that is also a heat pump, it'll work in reverse. How do I know I'm looking at it? What are the telltale signs, Pat?
Yeah, well,
$1 million question.
It's going to look very, very similar. So there's going to be a coil inside that looks very similar to air conditioning coil. And there's going to be a box outside that has a fan in it that blows air over a coil. And it's just with a reversing valve in the system, and generally the compressor's outdoors with the coil that's outside. With this reversing valve, they simply are going to change the inside coil from an evaporator to a condenser coil. And you're going to change the outside, what used to be a condenser coil in air conditioning mode, to the evaporator coil. So it's picking up heat from outdoors, and it's condensing and giving up its heat indoors, just the opposite of an air conditioner. As far as looking at it, yes, the outdoor unit probably looks a little different. The old traditional heat pump that we've, was introduced probably in the 70s when we started thinking about electrification of homes and whatever. The old, what we call the air source heat pump, and that's really still what it is. It's when we classify heat pumps, we classify them by where did it get its energy and how is it giving up its energy. And so in the case of an air conditioner or a reverse of the air conditioner or a heat pump, it's taking heat from the air and it's giving it up to air. So it's air to air heat pump. We can take heat out of water. We can put heat in the water. So then we have air to water heat pumps, and we can do water to water. So that kind of helps define, the working medium. So really is what it is. But the old air source heat pumps that we had back when forever didn't look that different from an air conditioner, actually. Pretty big unit outdoors, typically, that had kind of the same shape and whatever. And these reversing valve you don't see; it's kind of buried in the in the box. The new air source heat pumps, and certainly now as we move into what's called cold climate air source heat pumps, inverter-driven heat pumps. There's all kinds of terms that get used and thrown around here. They do have a different look generally. They're going to be more of a rectangular box and a different kind of front-facing fan, that kind of thing. So that's a pretty good giveaway. You have a heat pump if you see something that doesn't look like the traditional outdoor air conditioning unit.
Okay.
What I'm saying is it can look like an air conditioning unit and still be a heat pump.
And I asked because they can look indistinguishable. I've got a property that you two have both been to, our rental property, where you guys were using that for some training. And there was a time when was it? It was last fall, where it was like 40 degrees outside. I'm doing some yard work, raking leaves, and then the thing kicks on and it starts running. The AC starts running, and I'm like, what the heck? How is the AC running when it's 40 degrees and it's like 65 degrees? What the heck is this set to? And I go inside and it's set to heat. And I'm just scratching my head going, what is going on right now? And then the light bulb goes off over the top of my head like, holy cow, that's probably a heat pump. And I go back out there and I look inside. And like you described, Pat, when it's a heat pump, there is a reversing valve inside there, and you know, you're not going to know what it is. I'm not going to try to describe it, but if you go online and you Google reversing valve, you can see what they look like. It's an extra little thing that's going to be sitting inside of the air conditioner, and if you've looked inside enough of them, you know that this doesn't quite belong. And sure enough, I've got a heat pump in my house. I had no idea. And then I go back inside, and yeah, it's blowing warm air. And I'll tell you one other thing. That first time I came across one during a home inspection, I was like, oh, so this is a heat pump. I've read about these in books. Okay, this is cool. So, you know, normally you put your hand on the suction line on an air conditioner. It's going to be really cold. It might even condense in the summertime. So I put my hand on there expecting it to be warm. It wasn't warm. That was one of the worst burns I have ever gotten in my life, I think. When I put my hand on that, holy cow, that was hot.
Yeah.
Oh, my goodness. Tip for
I guess it wasn't the suction line, was it?
It was, no, that was the pressure line at that point.
Right.
And that thing was hot. So don't ever touch the big, thick line when you're running your heat pump on heat mode. Bad news.
Yeah.
That's all I got for you.
Yeah. Well, and like I said, it's the heat pump, you know, split system, whole house heat pumps have been around. And now what you have experienced there is a hybrid. So indoors, there's a furnace, looks like a furnace. When you have the heat on, it runs like a furnace. Sometimes. There's other times where it's saying, hey, I think the conditions are really pretty reasonable here outdoors. I'm going to take heat from outdoors with my heat pump and heat the house rather than using gas. And so that's really the whole impetus of what this electric, heat pump transition or movement is all about. Can we move from heating with gas to heating with a heat pump or electricity? And you have what we call hybrid system. Yeah, I've got both, right? So I've got so anyway, go ahead.
So help me understand, Pat. How does it know when to switch from heat pump to furnace or furnace to heat pump? How does it decide which one it's going to operate on?
That's where it gets tricky, and that's where it gets kind of proprietary. So all the heat pump manufacturers have different algorithms and different setups. Some of them are going to base it on outdoor temperature. And so you say, okay, I think my system will do fine down to this temperature, and then I want the heat pump to quit and my furnace to take over. There's some where they can work in tandem, not generally, but they can, where the heat pump continues to do its work, and the furnace comes on because the heat pump isn't keeping up. So that's a different control strategy. It's saying, gosh, the heat pump's working, but it's kind of slipping or falling behind. I better kick in the gas to back it up. Traditionally, we had heat pumps that, again, run by electricity. People didn't have gas available in some of these subdivisions or whatever that were built without gas. They were using heat pumps only. So you didn't have a choice for a gas backup. You had an electric resistance backup. And so within the indoor unit, sat a set of electric coils, toaster coils, if for lack of a better analogy, that would come on and boost the temperature when heat pump's falling behind. So again, there's lots of different combinations here, and there's a lot of different control strategies. Like I said, some of them they'd simply shut off. It's an on-off. Sometimes a homeowner can do it. They just hit a button and they move from heat pump mode to furnace only mode. The heat pump is going to give the signal that I'm done. Here it's ears, and then like I said, there's others where the heat pump continues to go, and the furnace just slides in behind to make it up. That's a little harder setup because now you got a furnace that's kind of interacting with this coil that causes some confusion that the manufacturers may not like. So that, like I said, that's where it gets kind of right down to a particular brand or a particular unit.
Okay.
The one thing to keep in mind, so with this conversation of the hybrid and or the backup need, and you talk more about cold climates, but heat pumps in general that are trying to heat houses, as it gets colder and colder and colder, the heat loss of the house, the load from the home, is getting bigger and bigger and bigger, right? The colder it gets, the greater the load.
Yep.
A heat pump that's outside trying to bring heat from outdoor air in, the colder it gets, the higher the lift. It's like a taller water tower. You need a bigger pump. And if you have a fixed pump, it can only pump so high. And so as the outside air gets colder and colder and colder, house load's going up. The capacity of the heat pump's going down.
Sure.
So they have this X where they cross and say, all right, now my load's gotten bigger than what my heat pump can produce. And that's kind of old school, and that's where the backup heat came in. The heat pumps that are being produced today they're trying to manipulate things in a way that they can still get a lot of capacity even at colder temperatures. And you sacrifice efficiency and other things in doing so, but they can go colder and colder and colder and still try to meet the load. And the other piece, I mean, it's getting a little far ahead or a little too technical, is heat pumps can be highly variable, like a furnace on off. Some people have 2-stage furnaces, on and on more, 2 levels. Well, heat pumps, especially the modern, we call inverter-driven heat pumps, and even the regular motor-driven heat pumps, can be variable capacity. And so what people will do is they'll oversize the heat pump a bit, but because it can go down much lower in capacity when the load is low, it can still do a decent job of cooling and dehumidifying, which we haven't got to yet. And yet when it gets really cold in the winter, it's got enough capacity to kind of bump up and meet the load. In particular, I think, for efficient homes. So that, we can kind of go into, well, where do heat pumps fit and where they fit well or maybe not so well. But that's just the fact of heat pumps. As the temperature gets colder, the heating load for the house goes up and the capacity of the heat pump goes down. And we're all trying to see how we can manipulate that in the heat pump. Well, I'd say manipulate the house. Get the house super efficient, and then you don't have to go to a huge you don't have to go to a huge heat pump to get the job done, and or you may be able to actually eliminate the need for backup heat.
So going back a second, I feel like, we haven't seen a lot of heat pumps in Minnesota. At least, when we're inspecting houses, usually we run across a, natural gas furnace or a boiler that does the heating. But occasionally we run across these heat pumps, but we're starting to see more and more of them. And I think we definitely have seen them in the capacity for cooling. Houses that don't have ductwork systems, that have boilers, and they want to add some sort of air conditioning, then they'll add these mini splits or these heat pump systems to provide cooling to the house. So I feel like those are, more common and becoming more common as we update houses. But would you say that that we are going to be seeing more and more heat pumps used for just heating too in houses moving forward in cold climates? Is that going to be the most efficient way to heat houses, you think?
Well, efficiency is a big word, but when we provide the heat we need in houses in Minnesota with a heat pump, yes, with what we call today's cold climate air source heat pump, absolutely. Yeah, you introduced another piece of this in terms of kinds of units. There are heat pumps that are more like the traditional split unit, where there's outdoor unit and then an indoor air handler that looks maybe like a furnace, and it's providing a whole central heat and cool for the whole house. And then we call these mini splits, where they're typically smaller units that have an outdoor unit and then an indoor head that's sitting in a particular room. And so that's another advantage, if you will, of these, is that, you don't have to have a ductwork system necessarily to move to a heat pump. And then it has the advantage, of course, of providing cooling, and then you can kick it in and provide heating. So we'll see people doing that where they might have rooms that have typically been cold. One of Pat's pet peeves are rooms over garages. Yes. And they're just notorious for heat loss, and they're notoriously bad for getting enough heat out to them. And so somebody will spot one of these in there. Now they have air conditioning, more comfortable in the summer, and they've got ability to pop some heat in there in the winter. So those units have been moving into apartments, other applications for some time. And now, like I said, they're being retrofitted into houses where people either don't have the central duct system and want to get air conditioning and can at the same time take advantage of them for a little bit of heat. I think, we're going to see, some of these now come into central systems, like, Reuben is describing with that house of his. But now to your question, why would somebody do this? So I look at it in three ways. Am I trying to save energy? And that's a very difficult question because you have to decide how you're going to count energy. And so for most people, the energy in the outside air, we're going to say, is free. We don't count that. It is energy, and we are borrowing it, if you will, or stealing it and putting it in the house, but we're not going to count that. We'll just count the energy in the pump, the heat pump, that is needed to move that energy to the house. And in doing so, you get what we call coefficients of performance that are greater than 1. You buy 1 unit of electricity, and you might get 1.5 in really cold weather units of heat. You might get 2, or if it's really 40 degrees outside, like the Reuben's example, you might get 3 or 4 units of heat for the 1 unit of electricity that you used. So that's coefficient of performance, and that's one reason people look at these is you think you're getting something for free, but in a way you're paying for it. The second part is people say, well, I want to save money, and I'll come back to that one. Another reason people do it is they're concerned about fossil fuel emissions. And that's really probably the primary driver right now of the transition from gas forced air to potentially
electrification.
Electrification, air source heat pump, central air source heat pump. And so, yes, if the grid is relatively green, or maybe you're using your own solar power and a few other things, you can look at this system, from a very high level, kind of house and equipment and electric generation grid, and say, I think I produced less CO2 in the atmosphere for my 1 unit of energy than I would have had I burned natural gas. So that's probably that's at the very high level, the climate change and fossil fuel emissions level and policy level changes is trying to promote and encourage electrification. And one way to electrify, or not, kind of degasification is what it is. It is a way that we can heat and cool our houses. And by the way, we can also heat our hot water this way too. So that's the move. The thing is, right now in cold climates, even with the superior technology that we're seeing today, and what we call an inverter driven, that's really just a fancy word for the motor. Some is acting slightly different, and it has this variable capacity, easily variable capacity thing that we talked about earlier. That they can be quite efficient, and they can change their load characteristics and things to try to match up the house in different ways.
It can be modulated,
et cetera. Yeah, they just become a viable candidate. The problem is, even with that equipment in a really cold climate, when it gets cold and there's not as much energy in the outside air, or you have to lift it further, it's going to cost you more. Current prices, it's just simply going to cost more. And then that kind of wraps. So people say, am I helping the environment? Most likely, yes, unless you're you're using a very dirty grid. Am I saving energy? Well, energy is a very hard question, but yes, you probably are saving energy at, we'll call it at the house meter level. And then, am I saving money? Well, when it's working really well, yes, and when it's struggling a bit, probably not. And that really brings us back to this idea of the hybrid. So people, when it gets cold and its capacity goes down, its efficiency goes down, its output, its capacity is down. What it means is it's sending less energy to the house. The air coming out of the vents is going to feel cooler. It isn't going to keep up, perhaps, depending again on all the sizing issues. And so that's kind of the downside, if you will, is darn it, it's not doing the job now when I really need it. And so that comes back to, well, should we be looking? And then people say, well, I'll put in electric strip heat. Well, that's COP of 1. 1 unit of electricity, you get 1 unit of energy. And a power plant, when they send a unit of energy, I keep kind of doing this not from a true technical physics level, but they send you 1 unit of energy, they burn 3. So think about this. The power plant burned 3, sent you 1, you put 1 in your heat pump. If you don't get a COP of 3, you went backwards.
Okay.
Right? And so, some of that 3 might have been wind or solar, and there's some other things going on if we want to get down and really try to compare emissions to emissions. But I'm just saying that, you always got to remember what's behind the electricity that's feeding that motor. And there's a whole set of downstream things happening there that most people don't, understand or appreciate or look into very deeply. It's just, here's my meter, here's what it read, and here's what I'm paying, for electricity. So anyway, I was saying this system has another system behind it. It's, gas does too, right? You have to pump it out of the ground and pump it to, through pipes to wherever it's going. And clearly there's an efficiency loss. You can't burn 100% efficient. So both have their issues, if you will. But I think that's why we're struggling with this idea of, well, geez, how does the heat pump fit? And back to hybrid, if the heat pump's hitting COP of 3, or better, you're doing well on energy and emissions, and you're probably doing fine on cost, what's it's costing you. But when you slide down colder, you lose that. You say, well, gosh, should I have a backup? And I don't think the backups, you don't want it to be electricity. And so that's when gas starts to look better, and that's where the hybrid starts to look better. And then you go, well, that's kind of silly. I just bought 2 systems. I got a furnace and I got a heat pump. And that's there's this great argument, kind of what people, the climate policy and climate advocates are saying, we need a revolution. And I'm going to say, I think we need an evolution. I think we need to move, from what we have to where we'd like to be, and maybe a little more, step-like fashion. And I think the hybrid does that. Here's the irony of the whole conversation about, hybrids and moving that way. I simply don't understand why anybody is putting in an air conditioner today.
Go on.
It makes absolutely no sense, right? It's the same equipment. You've got a compressor. You got 2 coils. You got, I added a reversing valve, and you added some complexity. I'm not going to, try to overstate this. Now, people suggest that it's probably a few $100s more. Now, if you go out in the market, they're probably going to charge you a few thousand more. For the same size, air conditioner versus heat pump, which is just, the market's not there yet, and that's a whole other conversation in terms of the HVAC contracting base and the delivery, the market to deliver heat pumps to the customer. But in my mind, and that's what happened in my house. So now we're back to kind of personal experience. My air conditioner went out. It's like, well, this is silliness. Well, I'm not going to put an air conditioner back in. This is when to make the transition to a heat pump. Now, my house is a little different. I was heating a little differently with what's called a combi. I was using hot water coil, fan coil to heat the home, and I can put my air conditioner on top of that. I can put the heat pump on top of that. So that was the time to make the transition. And think about how many air conditioners have gone in the last, this summer or the last few years. And there really is no reason why they couldn't have all been heat pumps like what Reuben had in the house that he purchased.
Huh. You're saying this now, and I just replaced my air conditioner and furnace at my primary residence here a few years ago, and I'm thinking, why didn't I do a heat pump? I don't even know. It wasn't even on my radar. I wasn't even thinking about it. But now after this conversation, I'm thinking, I feel like I'm kicking myself. Like, why didn't I price that out and talk to a bunch of different contractors?
Yeah. If you priced it out, you probably would have wanted the same decision. Unfortunately, like I said, it's just not. It's not as close as it should be yet. There's hesitancy on the HVAC contractor trades on heat pumps. Like I said, they've been around forever. They've put them in. Some of the early ones, air source heat pumps, what I call the originals, were going into houses, in central U.S. and further south, right, where there's primarily air conditioner and a little bit of heat. They all worked fine, but as you got colder and colder, there were some poor experiences, and contractors, kind of got nipped a little, and they're a little nervous or a little afraid of the technology. So the contractors aren't quite there, and then they've got to figure out how to upsell somebody, probably at a point in time where the furnace just went out on them, and they're anxious to get heat back, or the air conditioner went out and they want air conditioning quick. The whole HVAC delivery system is very unique and different in that. Not very proactive. It's almost always reactive. And so, and we've lost a lot of skilled trades in the HVAC industry. They are trailing behind in a lot of ways. So it's just, like I said, it's not just an equipment conversation. It's also, is this the right fit for your house and your set of circumstances? And even if you got the right equipment and the right house and the right circumstances, do I have a trade base that can provide the product in a reasonable way, and with some confidence, and with the reason, cost effective or affordable manner. So there's a lot of pieces that have to come together.
So Pat, kind of what I hear you saying is that technology's improved. So now that, so cold climates like Minnesota can use heat pumps for heating and cooling, and that's effective. And you don't have to have a backup system installed at the same time.
You don't have to have a backup installed if you have an efficient home.
Okay.
Where the load just doesn't go crazy on you when it gets cold, right? If you have an old leaky house and the wind's blowing and, it's just losing heat right and left, the poor heat pump's just going to struggle. I mean, you just get a bigger and bigger and bigger heat pump, but, you're not going to be happy. Whether it's the cost of the heat pump, right? The equipment's going to be twice as much. The operational cost is going to be higher. So, So that's back where I talked about kind of the right fit. But if you have an efficient home, yes, we can get heat pumps. There's several of us who have run, entirely on heat pumps in relatively efficient homes. Myself, Gary Nelson, others. There's a number of places around Minnesota where they have satisfactorily heated their house in the winter with a heat pump. If here's the other little piece of it. It's kind of a little back secret of it is, if you're running your heat pump and you had your temperature set at 72 or something, and it starts to slide to 71 or 70, or you're getting down to 68 or 9, and you're not happy, just turn on some lights.
But, we can't use incandescents anymore. We only have LEDs.
I know. But
turn on all your computers and your TV
and your TV and your
oven.
A little electric heater. Now that is electric resistance heat, of course. It's 1-to-1. But I'm saying you can take that edge off of that
with internal gains.
With internal gains, right? And so you may end up doing that for a few hours a year. Whereas in the past, when we were doing backup heat and air source heat pumps, they were quitting at, they were designed to shut off at 20 degrees.
Yeah, that's what I remember.
You were on backup all the way down to minus 15 or whatever, right?
That's what I associate heat pumps with still. Yeah. So that's why it's interesting to hear you say that, they've come a long ways, the technology's advanced so that if you have an efficient home, you can heat it with just a heat pump. You don't need a backup. But there's a lot of old homes here in Minnesota that are not to that level and they would need a backup heat system.
Yeah. So our current heat pumps are going down to zero. The cold climate air source heat pumps should be able to operate down to zero pretty effectively, and many of them will go below zero and continue to run and continue to be above 1 COP, probably 1.5, 1 point, whatever.
Depending on the efficiency of the house.
Right.
And you talk about having a newer, more modern, energy efficient home. Do you feel like there's an age of home where we kind of cross that threshold where you might say pretty much any house built after 1994 will probably be efficient enough? I mean, is there an age of home where just a cookie cutter new construction built to the current energy code at that time would be enough where you could put in a heat pump without additional modifications to the home?
Yeah, I'd say there were certainly houses built in the 90s under the 91, 94 in Minnesota, under those 1990 codes that were built above code.
Okay.
And are tighter than what code would have allowed at that time.
Okay.
They're certainly candidates. There's some houses built in the 90s that still were pretty leaky, maybe really didn't hit the mark on all the insulation levels, or extravagantly large, or have lots of exterior surface area and a bonus room over the garage and whatnot, that you still kind of say, well, can we really, and you can. I mean, you could replace the central unit, and it's just sizing. It's just a sizing issue.
Mm-hmm.
But yeah, you're looking for a newer home, an older home that's small, and has been weatherized to be relatively tight. Might be a candidate too. So it's and certainly those are good candidates for the hybrid, right? Because they have an existing furnace, or they are going to need some backup or whatever. So I think in my mind, I guess that's back to this kind of evolution approach, is you kind of start sliding those houses to more and more efficient shells, and then that sets them up to be a good candidate for a heat pump. And then, of course, watching their equipment cycle, the furnace goes bad. If somebody's furnace goes out, somebody's probably going to try to talk them into a new air conditioner coil, because they got to pull it all out anyway, right? Whatever, because the furnace cabinet's going to be different size and all these things. And so then they're throwing in the outside unit. Well, now they should have a furnace and a heat pump instead of a furnace and air conditioner. So there's a pretty easy, logical evolution, transition there, even in our older homes. It just doesn't make sense. The old days, when I first started in this business, I was heavily into solar energy, passive solar, active solar energy. And, we always told people it makes, no sense to try to solar heat a corn crib, a barn. It makes no sense at all. Conservation is so much more efficient, so much more controlled, so much more cost effective. You bring the load down and then you implement. And that's really what this is about here, is long-term thinking about bringing the building shell back into better control and better compliance to kind of modern standards, and then sliding the equipment towards the new generation of heat pumps.
So Pat, how long would you say that kind of this newer technology of a heat pump that can heat a cold climate house when it gets to 0 degrees outside has been around for? Is this like the last 5 years, the last 10 years, 20 years?
So the mini split was kind of the introduction of the new version of heat pumps, and that was being used for retrofitting older homes to get, heat, air conditioning into certain rooms and whatever. And then they said, oh, by the way, we could heat that room too. So those are 15, 20 years old in apartments. So the other thing is, I was talking about examples earlier. Almost every hotel room you've ever been in is a heat pump.
Okay.
And they go back 40, 50, 60 years. What's called a PTAC, package terminal unit, package terminal AC unit, that would sit under the window and rattle all night and provide air conditioning. And then they might have electric resistance if they needed some heat, or they might have had a baseboard maybe back then or whatever. But pretty soon, again, somebody said, hey, what if I just put a reversing valve in here and then heat with that? And so, any hotel room that's going back probably 20, 30 years has a heat pump in it, provide heating and cooling.
Okay.
So I'm just trying to catch up. I mean, it seems like you said, our industry is lagging behind. A lot of the HVAC contractors were, like you said, kind of, had those challenges before with the older systems that maybe couldn't keep up. And they're afraid to work with the newer systems and to try this newer technology, even though, quote, new is 20, 30 years old.
Yeah. Yeah. And the very high end cold climate inverter driven heat pump, it's more 10 years plus 10, 15 in the market.
Okay.
So, it's slightly newer than, say, the PTEC unit I was just talking about. And again, it was kind of a specialty thing. And so again, there was contractors that used them on, a spot here, a spot there. It certainly wasn't a market transition. And now the equipment options are such that, there could be a pretty general transition here over the next decade.
Okay. So I want to ask you, so in your opinion, it makes sense for people to be thinking about using this type of technology, but in reality, it might be difficult to find a contractor who can install this, but it's available. And if you live in a cold climate, even you can have use a heat pump and take advantage of that.
Absolutely.
Backing up though, I just want to ask you, what do you think about ground source heat pumps? And we've been talking about air to air heat pumps, but what about water to air heat pumps, or like a geothermal system? Do those systems still make sense? Are they a smart investment?
Two different questions there. They make a ton of sense. So again, when you think about trying to strip heat out of 15 below air, it's kind of a challenge.
Yeah.
And if you're down on the ground and the fluid that you're circulating out to the ground loop is running even 25, 30 degrees, it's going to be a water glycol mixture, antifreeze mixture. It's got twice as much available energy, right, as the air outside does. So they're remarkably efficient. Energy-wise, they don't lose their capacity the same way, right? The ground's it's getting colder as you're using heat from it, but it gets replenished, and to a certain extent. And so it maintains its capacity pretty well all winter long. And then if you think about this, in the summer, you're pushing heat out there to heat up the ground that you're going to turn around and take out next fall, right, in winter. It's a remarkably efficient system. And there's another advantage to it in that the equipment is in the water mode. It's easy to get hot water off this with what's called a desuperheater and heat your hot water. So now you've got really efficient heating. You're heating your hot water. Your air conditioning is practically free because you're dumping heat from the 75-degree house into a 50-degree ground or whatever, right? It's just remarkably efficient. So air conditioning's, very, very high performance, but it's just the cost. So that's where is it cost effective? The fact that you have to put in this ground loop, you have to have the area, you have to have the expense of going vertical loops with a well drilling equipment, or you can go
feet down usually.
Yeah,
right?
probably 250, 300, something like that. Yeah. You can probably stop at 150, but the further you go down, the higher the efficiency and the less wells you need. And so to maintain your capacity, or you go with a horizontal system, and there's lots of different versions of that. Now the trick here is now we've got inside equipment that has to get married up with the outside field. It's not just air blowing around, right? It's a very intentional heat sink, heat source that you're building, and that has to marry up to your house. So there's another contractor involved, and we've seen, where that's been issues of, the ground loop just simply wasn't done properly. They typically undersized it because it costs so much. And now we have undersized outside ground loop, and then we lost some more efficiency, et cetera, et cetera. So I love ground source heat pumps in theory. And if I had the money, that's what I would use, because again, it's just a marvelous application for a heat pump. It's really just it's a cost, and then having proper area to do what you need to do. And with vertical wells, it doesn't take much area at all. And good installers is really critical for the overall efficiency and performance of the system. Yeah, love it. So it's just, now here was the challenge. The flip side is people thinking about ground source heat pumps for people building new houses. And if you build a super efficient house, how much can you afford to spend on heating it or cooling it? So that's kind of
The
a
loads
reverse.
are so small, then why would you spend 50 grand on a
Yeah,
geothermal system?
yeah,
You'll never
exactly.
see a payback.
Yep.
Yeah.
And so that's why they kind of started to slip a bit.
Okay.
And the air source heat pump technology was coming on, and it looked a lot cheaper and easier, maybe less issues with installation, maybe. I'd say qualify it maybe. They just kind of took over, and the ground source heat pump slipped a little. So that's back to my original point, was heat pumps are our future. It just makes sense to take heat from some place that has excess and put it in your house. So whether you're using solar energy in some way, using ground energy, or the air, that's kind of the last resort, but it's the easy resort. You can think of buildings all over the place where one side the sun's beating on it and it's super hot, and the other side getting a cold northwest wind and it's cold. Well, heat pump just moves the heat from here over there. Bingo, done. Super efficient, super easy. So they're here to stay. It's just we need to work with our trade base, and we need obviously some consumer education as to what it is, how it works, and before we see any kind of mass transition.
Wow. And would you say the majority of people in the South are using heat pumps already, or would you say that they're using just your standard air conditioning system because they don't really need heating?
Well, they're making the transition much faster. You'll still see furnaces, central air system, central forced air in the South, and they'll use gas because it's cheap. It's probably even cheaper in the South, right?
Yeah.
But again, the heat pump makes such sense for them because it's going to work way efficient in the heating mode. And then, of course, you need air conditioning, so you'll be there for air conditioning. You're going to have a higher air conditioning load than heating load, presumably, so you have to, have a bigger unit, which means it can do the heating load very efficient because there's a lot of, a lot of coil on both sides, right compressor or whatever. So, it should be almost automatic in the South. It's not there yet, but it'll clearly transition much quicker there. We'll see.
And they're great for everywhere in between the South and the deep North.
Oh yeah, in the what we call the Rust Belt or the Rot Belt, the in between. It's a great fit. And the whole thing that's going to make this work is the fact that they are so variable, or they can modulate so well.
Yeah.
Because here's one last little piece that's really important with heat pumps and air conditioning. Traditional air conditioning oversized led to houses that were cold and clammy. Mm-hmm. They had high efficiency. They could cool the house, instantly, but they didn't wring out the moisture. So to wring moisture out of the air, and a lot of people say it's not the heat, it's humidity, and there's some truth to that. To wring moisture out of the air for comfort in a home takes a lot of energy, actually, and it takes a very long cooling cycle so that lots of air can move over that coil and condense. Now you can slow the air down. Slow down too much, coil freezes up. That's not good. So what typically has happened is to get the efficiency of the air conditioner up, they move far more air across the coil, end up with a far warmer delivery temperature, and that gets you maximum efficiency and minimum condensation, minimum moisture control. So that's been a game of trying to show higher and higher seasonal energy efficiency ratios from an energy standpoint, and compromising and sacrificing moisture control and comfort big time.
Sure.
And everybody was oversizing air conditioners anyway, and now they oversize a very high efficiency air conditioner, and you just get zero moisture control. So we've been trying to tell people downsize, or go to variable, a 2-speed or a variable capacity air conditioner, so that you can in fact wring the water out when you want to wring the water out.
Yeah.
Well, what we say about the heat pump? One of its prime advantages: highly modulating, highly variable capacity, And they've got all kinds of brains inside the system. Sometimes they outsmart themselves, but they got the brains in there to be able to say, oh, let's slide into a dry mode here. And I'm going to slow things down, get the coil a little colder, and strip more moisture out on its way by, and provide less what we call sensible cooling, or the temperature of the air is not going to be as cold, and there won't be as much of it because they slowed it down to meet the sensible load of the house. And so there's just this huge advantage again of good equipment and good installs, where you can actually get better humidity control out of this heat pump, because you can oversize it to meet the heat load without compromising the summer comfort. Again, if somebody's smart and they're playing the right rules and doing the right calcs, doing their load calcs and their system sizing properly, you don't compromise that summer comfort as much if you happen to oversize a little bit to cover heating. So, down south, that's the opposite, right? It's got more cooling, less heating. They're in great shape. Up here, we might size a little large for the heating, because we don't have a backup, and that could compromise the cooling. But if it's a smart system, it shouldn't. So, that's one of my pet peeves is air conditioning oversizing and poor dehumidification this summer. It's a far bigger problem than anybody realizes in terms of comfort. It's a far bigger problem than anybody realizes in terms of mold growth and indoor air quality. And so, again, with some, fingers crossed and some positive thoughts, I think if the trades will pay attention here, we can move into where we use heat pumps and actually get better air conditioning, better dehumidification. And so that's another plus.
Yeah, that's a huge benefit that we don't have the same problem with oversizing ACs and having humidity issues with heat pumps. You can have a modular system that gets the humidity out but still meets the demands.
Yeah.
That's great.
And the other transition that I'm sensing here is we're going to slide away from the mini split, which was kind of somebody's not going to be happy here, but kind of a Band-Aid approach to introducing heat pumps into certain marketplace rental units and hotels and whatever. And hotels probably will stay there. But I like central forced air. I'm just a huge fan of central forced air in buildings. It provides
for filtration purposes.
Filtration, circulation, a bit more uniformity, more comfort. It just has so many advantages for providing overall comfort in that house. And you can get fancy and put more heat or cooler here or there wherever you need it. So all kinds of things you can do with that system, and provide a way to distribute your ventilation air. To all the rooms, your bedroom where you spend all your time, right?
URVs can tie into it.
So I like central forced air systems, and now there's no reason why we can't have a central air source heat pump system that provides, air conditioning, of course, heating, and dehumidification properly done, right? So that all starts to package up, and then I'll just kind of take the next step out is, well, what if we had an air source heat pump that could heat water or heat or chill water? So I got two tanks in your house, a hot water tank and a cold water tank, and a heat pump that can move heat from outside into the heating tank, or from the cooling tank to the heating tank, or from the cooling tank to outside. And now we're managing the system for the maximum efficiency. And then you move that hot water or cold water to a coil in a air handler. And now you can heat and cool and dehumidify and have hot water with a single heat pump
system that you used to have in your house, but with a heat pump instead.
Yep, absolutely.
So that doesn't exist yet?
It does. There's a lot of people looking at it. I mean, there's some compromises that have to be made when you're trying to cool, chill water and heat water. What refrigerant do we use? And there's some issues. But I'm just saying, back to this idea, heat pumps are our future, and I don't think we've even thought about yet, how clever, how the applications and how clever we could be to be super efficient in moving heat around with a heat pump. And it comes with complexity and controls, and so there's always challenges there.
has a long ways to go, I think.
Yeah.
If you have to teach them that they can install them in a cold climate to heat a house.
That's true. Yeah, we better
Step
start.
one.
Step back. Baby steps. Yeah, let's start there.
Baby steps, man. Well, Pat, we covered a lot of ground today, and you answered a lot of our questions. And I think my key takeaways is that heat pumps do work in cold climates. The technology is there. It's the HVAC industry. It's kind of trailing behind. And so it's harder to find installers who are confident and competent installing them, and that they're priced affordably, so it makes sense. But the technology is there, and depending on the size and kind of efficiency of your house, it could be a system that you could look into in the future when you're thinking about upgrading. And so I think that's a key takeaway for me. And it's something that, we as home inspectors, and for me doing the house coaching, I come across a lot of people that have systems that are kind of approaching the end of their life expectancy. And they're like, okay, what should I do? And it's like, well, let's think about, does a heat pump make sense?
Yeah.
One other thing we had on the list was, do you need to elevate the outside unit? And absolutely, in cold climates, you don't want the unit sitting down in the snow.
Okay.
And so, they all should be sitting on a stand to get good airflow. Air conditioners as well need good airflow and keep your bushes away and things like that. This thing is trying to transfer heat from outside in, or in the summer inside out. It needs airflow around that outdoor unit. So always have good airflow around that unit. And in the winter, you're going to try to steal heat, and if there's snow on the ground, you want to be up above it. The one other little piece of that I'll just mention is, people might be surprised, is in the winter you may see condensation and water running off your outdoor unit. Well, if you think about what it's doing, it's chilling that outside coil down below the temperature of the outside air. That's how heat moves from warm to cold, to the cold fluid. And that cold fluid picks up the heat, right? And will be moving it in through the heat pump. And so the coils get colder than outside air. And when that happens, you can have condensation or dew. And if it's above freezing, if it's below freezing, it'll be frost. And so these outside units do go through a defrost in the winter to clear the frost off the coils if that condition exists. And you'll see water dripping off, or you'll have ice underneath of it, or whatever. Another reason, again, to have it elevated.
Sure.
Those are some more helpful clues for home inspectors or homeowners trying to identify what type of system they have. Yeah,
if the outside unit is sitting on stilts, it's just not a guarantee you've got a heat pump.
Yep, absolutely.
And if it's not, it should be, apparently.
Yeah, totally. Yeah. It's just, if it depends a little on location, if it's protected from snow drifting, and there's some advantages of having it on the south side. If you're thinking about, you're really trying to push its heating capacity a little bit, it's not much. That hurts the cooling side a little, but not much. Yeah. So, there's some things about where you put that unit too. And again, that's kind of back to installation and sizing and proper.
Okay.
How many contractors actually understand that?
Or homeowners, contractors says, it'd be better here. And the homeowner says, no, I don't want it there. I want it over here on the north side. So it's, that's a whole other conversation about building design and and maximizing your equipment efficiency or whatever, regardless what system you're using.
Yeah. Well, thanks for coming on, Pat, and myth busting for us a lot of things about heat pumps that, some things that I didn't understand or know about them as well today. So I appreciate you sharing all of your wisdom and knowledge with us today.
Yeah. Thank you so much for coming on, Pat. Always a treat to have you on.
Yeah, I enjoyed it. Yeah, I appreciate it. And good luck. I hope folks can kind of start to learn more about it, as well as our contractors, and make this transition as easy as possible.
Yeah, love it.
Agreed.
And for our listeners, if you got any questions, Tessa and I surely will not be able to answer them. But you're welcome to email us anyway, or any thoughts. We love your emails. You can send them to podcast@structuretech.com. And if you want to get a hold of Tessa directly, I have a link to her website and all that contact info in the show notes as well. So, Pat, thanks again for coming on. Always a pleasure. and we will catch you guys next time. Thanks for tuning
Thanks.
in. Take care.
You bet. Thank you.